Okay. So last time, so we discussed how to define so-called the general power functions. So general power functions. So if for non-zero complex number, this is going to be our base of the power function. And for any complex number C, we have the z power of C is defined to be e to the C times ln of Z. So this is our definition. So, well, as expected, so this is a multi-valued function. Anyway, so this is our definition because, well, we want our general power function to somehow an extension of the real version of the power function. And if you think Z and C, if they are all positive real numbers, if Z is a positive real number and C is any real number, then you can easily convince yourself that this definition actually coincides with the real version of the power function. Okay, but in our case, but in the complex analysis, the power function is, well, has to be because the definition involves the complex logarithms, so therefore it has to be the multi-valued function. So today we're going to discuss about its branch. So properties. So first, this is easier one. Z to the minus C power is, this is just simply 1 over Z to the C. So why is that? Because if C is, well, if we put additional negative sign in front of this number C, then, well, then this guy is going to be e to the negative something. And when e to the negative some complex number can be considered as the reciprocal of that. So because the reason, so, well, this equality can easily be justified. And number two, and we also want to discuss the derivative of, anyway, so in order to discuss any derivative for this multi-valued function, then first of all, we have to actually choose a branch of this function. So, well, just choose any branch of the function. So choose a specific branch. Of natural log. So Z is positive, and we say the argument is between alpha and alpha plus 2 pi. And once this branch has been chosen, then its derivative is, well, C times Z to the C minus 1. Okay, so this one looks like, for me, this one looks like a very familiar power rule that we have studied in the single variable calculus. Okay, so why? So I want to compute the derivative of this guy, but because of its definition, this is a composition of two functions, exponentials and some constant times the natural log. And we have the chain rule for we have the same chain rule for the complex analysis. So therefore, I can use the same chain rule. So the outside function just carries over times this inside function taken derivative, but, well, however, we have chosen our branch. So therefore, the derivative of this function is going to be just C over Z. And yeah, so then we are almost done. So C times exponential of C, L, and Z. And I have Z in the denominator, but please allow me to write this guy as the exponential of ln of Z, right? And then now what? So, well, you know that exponential of some number divided by exponential of another number can be written as the exponential of C ln of Z minus ln of Z. But yeah, so I can actually simplify this ln of Z. So this is just C times Z to the C minus. Okay. So this is a power of the complex version of the power law. And number 3, we can also discuss the derivative of the exponential function. So again, so we choose a specific branch. Branch has been chosen. Then the derivative of this time C to the Z is C to the Z times natural log of Z. So again, so this equation is also very familiar to us. So this is just nothing but the derivative of a general exponential function. So taking the derivative, so this is so exponential of Z ln C, right? So I am taking the derivative again. I must use the chain rule in this case. So outside function just carries on, but the inside function just Z times ln of C, but ln of C is a just constant. So ln of C. So yeah, so weird. Okay. All right. So now we know how to take a derivative of these functions. Just before we finish this section, so I want to introduce the notion of the principal value of the general power function. So what is that? So well, speaking of principal value, so that reminds me of the principal branch of the natural log function. So do you remember that? So what was the principal branch of the natural log function? So that was, well, when argument has been restricted between minus pi to positive pi. That is what I meant by a principal log function. So likewise, if I say the principal value of general power function, or sometimes I will just say the principal branch of general power function is this is just e to the, as you can easily expect, not just ln, but just large capital letter Ln of Z. So this is our version of the principal value or principal branch of the general power function. Okay, all right. Oh, before I finish this section, just one more redundant remark on involving our convention on the natural log function. So from last lectures, we have been talking about the natural log function, and from time to time, you can see some expressions like this. Many authors in complex analysis, they are abusing notations and they are using expressions like this. What does it mean? So, well, unless the branch has been specified, so this left-hand side is this is not a number, but this is a set of numbers, and this is also a set of numbers, and this is also a set of numbers. So what does it mean? So what does it mean by these two guys are the same? So that means, well, our convention is once you have chosen the argument, so well, in these expressions, you can think of the argument of three different complex numbers. Argument of this number, and argument of that number, and argument of this number, right? So, well, in this expression involves the three different arguments, and this equality means once the argument of two complex number from these three were chosen, then the argument of the last one is automatically determined. In this sense, we are using this equality. Okay. All right. So just a redundant remark. This is just a digression. Okay. All right. And okay, so we are done about complex functions. And finally, we are turning to chapter 14, which is about the complex integration. Well, maybe I'm good to turn to the next page. So chapter 14 about the complex integration. Okay, so there are many, well, so complex integration. So, well, what is a complex integration? So, well, as speaking of integration, so in our mind, so that basically reminds me of the integration is an inverse operation of the derivative. So once you can take a derivative, then the integration is like something like, at least in my mind, that is an anti-derivative, right? So actually, in fact, well, in some sense, that is even true in complex integration. But in order to justify the statement, then actually I have to introduce many notion of the complex integration as a line integral. So do you remember the line integral? So what was the line integral? So when we were studying the multivariable calculus, then we studied the line integrals. So integrals, so if you have function on 2 dimensions and you're supposed to draw any curve or contour on the plane, then you are supposed to perform an integration along the curve, right? So that is supposed to be the line integral in multivariable calculus. And in this chapter, we're going to do not precisely the same, but we are going to do almost the same thing in the complex integration. And in order to do that, then first I will start from the easiest version of the complex integration. So our first topic is going to be, we want to take a derivative of function w of t. So, okay, so first I will need to explain what do I mean by w of t. So what is w? W is a function from R1 to R2. So W should be considered as, well, first you can consider W as a curve, 2-dimensional curve, right? But, well, sorry. But I should better replace R2 by C. So this is just a complex values function. So, well, this is a 1-parameter family of complex numbers. Okay. So, all right. So therefore, W must be depending on a single parameter. I will say T. And this is a complex number. So it has the real and the imaginary part, which I will call UT and VT. Okay. So, well, I must be able to write down W as a sum of these two functions. Okay. And Well, and suppose that these two functions, u and v, are differentiable in calculus, in single variable calculus sense. So if u and v are differentiable in the sense of the single variable calculus, then we define just like. So, well, you can consider this is nothing but a velocity vector. Okay. Right. Okay. Well, actually, I'm okay about this notation. Well, so I need to say something about something on the notation of the differentiability. So, well, I am right if I say W prime, then that somehow reminds me of the complex integrals, complex differentiation. But this is clearly not a complex differentiation. This is just a real differentiation, right? And in order to distinguish between these two, so please from now on, if I want to say something about the real version of integration, sorry, real differentiation, then I will just say I'm going to use the physicist notation, which put a dot on the bottom, on top. So just notation. So in order to differentiate between these, between the real and the complex differentiation. Okay. Okay. All right. So this is a small warming up exercise. I have a complex number, Wt, and I take a square of that number. And I claim this is 2 times Wt times W dot of t. Why? Well, this is just a matter of tedious computation. So W of t squared is ut plus I times Vt. And you take a square of this, then this is going to be just ut squared minus Vt squared and everything plus I times 2 times ut and Vt. And if you take a derivative, then this is going to be you take a derivative of you take a real version of the derivative to the real and the imaginary part, then you can easily convince yourself that Wt everything taken derivative then this is just, you can easily say this is just 2 times ut plus I Vt times u dot t plus I times v dot t. Okay, so yeah, so this is just a matter of computation. So. Also, I have also very easy exercise. So if I take a derivative of e to the some complex number z0 times t, then you can also easily see that this is just z0 times e to the z0 times t. So the same, just same thing. So well, this is just well, not very surprising because we are just borrowing all the notions from the real differentiation. So the result also must be something that you can easily expect. Okay. Now, I want to talk about the derivative of this W of t, the one parameter family of complex numbers. So definite integral of well, again, assume that this is my complex number, a one parameter family of complex number, W, and also assume that U and V are continuous on some closed interval, which I would say just A, B. Then, well, I can finally define the integration of this complex one parameter family of complex numbers as, well, not a big deal. You take the integration of the real part plus I times the integration of the imaginary part. That's it. Okay. Okay. Not very surprising. So since we are borrowing exactly the same notion of the integration from the real version of the calculus, therefore the result would be the same thing. Suppose that I want to take an integration of this exponential function. Then this is, well, I'm going to split this guy into the real and imaginary part. So this is cosine t plus I times sine t. So this is, according to our definition, this is sine t evaluated from 0 to pi over 2 plus I times minus cosine from, again, from 0 to pi over 2. And it turns out that this is, what is this? So square root of 2 over 1 over square root of 2 plus I times minus 1 over square root of 2 and plus 1. Okay. Okay. Very easy. Oh, by the way, on the other hand, so I want you to verify this by yourself. And actually, this number is the same as 1 over I times e to the it evaluated from 0 to pi over 2. Okay. So how did I get this number? Well, formally speaking, so this expression is just actually turns out to be nothing but the entire derivative of this guy, right? So, well, because since our rule of the differential integration just, well, is exactly the same as the real integration, therefore I can actually use the same rule for the same rule as we used in the real version of calculus. This is the fundamental theorem calculus, right? So you find the antiderivative and you evaluate the antiderivative from these 2 points, then it turns out to be these 2 numbers of this. So in fact, if U and V are antiderivatives of, so these are real valued function, functions on A, B, such that U bar dot is U and V dot is V, then the integration of WT is just UT plus I times VT evaluated from A and B. So you can actually use the same rule. Oh, sorry. So I will define W to be, yeah, this one, this is more consistent expression. Then this is a large W of T evaluated from A and B. So WB minus WA. So from now on, so if I try to integrate this one parameter family of complex numbers, and if this one parameter family of complex number, if this guy has a nice expression so that I can find its antiderivative, that, well, maybe I will just find its antiderivative and evaluate them, okay? All right, so this is the integration on the one parameter family of complex numbers. Well, it's not a big, yeah.
You're both calculation just the 1 plus I.
This one? Yeah. Maybe did I make any mistake? Yeah. 1 over I times e to the. So this is just minus I times cosine t plus I sine t. You're talking about this, right? Yeah. No. Well, which one?
The sine t and I minus cosine.
I minus cosine t. Yeah. Any problem here? No.
지수가 I 플러스 1이야. 지금 넣은 건 4분의 8번은.
Ah. Okay, thank you. I must be. Ah, right. Yeah. I was wrong from the beginning. Sorry. Yeah. In my lecture note, I tried pi over 4, but for some unknown reasons, I put pi over 2. Sorry about that. Yeah, thank you. Okay, good. All right. So this is it. Anyway, so this is, well, not a big deal. So as you can easily expect, so there's actually essentially no different from the real version of integration. Now, let me turn to the line integrals. So in order to say something about the line integrals for the complex functions, then first of all, well, we will need to discuss something about the line in the plane. So, curve in the plane. So, well, this one parameter family of numbers can also be considered as a curve in complex plane. So I will just write z of t is xt plus I times yt. And we are gonna, from now on, so unless otherwise specified, I'm gonna consider these two real and imaginary part to be continuous functions on the domain. So these guys are continuous. Okay, then then z of t can be considered as a parametrization of a curve in complex plane C. So, so this is, this function, this one parameter family of complex number, z of t. So this is not a curve, but I say this is, I want to emphasize that this is a parametrization of a curve, right? So do you know the difference between the curve and its parametrization? So curve is actually nothing but the image of this function. The image of this function is, curve is actually nothing but some subset of complex plane, which is the image of this function. And the parametrization is a function that maps from this closed interval to complex plane. So in other words, parametrization actually contains parametrization contains information not only about the curve, but about the information how I travel along the curve, right? So even if you have the same curve, but there are infinitely many ways to travel the curve, right? You can actually choose to travel the curve in slower way or faster way, and also you can choose to travel in this direction or that direction, right? And the parametrization contains the information about that travel, right? Okay. And the orientation. And of a curve is a choice of one of two possible directions for traveling on the curve. So, speaking of orientation, so once the parametrization has been chosen, then that parametrization, as long as the parametrization is one-to-one, then choice of the parametrization automatically chooses the orientation, right? So orientation actually doesn't care about your speed. It only cares about the direction, the way you travel, right? Direction that you travel. So that is the orientation. So therefore, there can be only two orientations, even though there is infinitely many choice of parameterizations, but choice of orientation is just two. And and also our convention is, I said the choice of the parameterization will automatically choose the orientation. So how? So in the domain of new parameterization, so which is the closed interval from A to B, and there is a natural way of increasing direction on the domain from A to B, and that increasing direction we're gonna give you the orientation of your curve, right? That is what I mean by choice of the parameterization chooses the orientation. Okay. When also we say a curve is simple if it does not have any self-intersection. And we say a curve is simply closed if the curve is simple and Z of A is Z of B. So in other words, has to be loop, right? Without any self-intersection. And also a simply closed curve is said to be positively oriented if the orientation is a counterclockwise orientation. Positively oriented if it is the counterclockwise orientation. No. Okay, so these are some terminologies on the curves on the complex plane. And we're going to talk about some easy example. Suppose that I have this z of t is z0 plus e to the I times t. And the data, no, sorry, not data. So if the t is between from 0 to 2 pi, then what do you think is this curve? This is a curve centered at the point z0, whose radius is just 1 and has counterclockwise orientation. Okay. What about these two? So z1t is just e to the minus it, and z2t is e to the 2 times I times t. So t is both from 0 to 2 pi over 2, 2 pi. So these two guys, they are the parameterization of the same curve, right? But for Z1, for the top one, so it parameterized the unit circle in negatively oriented manner. And for the second one, so it is actually parameterization of the unit circle, but this time around, so it travels in counterclockwise direction, and it winds up the origin for twice, right? So they are different. Okay. Also clearly, this is x dot t plus I dot t. So this is a velocity vector. So this can be considered as a velocity vector. So now we are ready to define the so-called path integral. Okay, so first we actually have to have a oriented curve. Also, this curve must have a parameterization. Xt plus I times yt. And t is from A to B. And if f is continuous function, so f is a function. So we say the function is integrand. And also we have to assume that this guy, the velocity vector, must be continuous. The z dot is continuous means that this x dot and y dot, they are both continuous. Then fz dz, this is a line integral. Is defined to be from A to B f zt times z. No, I should be put the dot on top of this. So this is called the complex line integral. Okay. This expression somehow reminds me of the line integral that we studied in the multivariate calculus. Okay. Not precise, but not precisely the same, but almost similar to the multivariate calculus line integral. Before I try to solve any exercise on this complex line integral, so I will need to make sure just one thing. Is this definition well defined? In other words, well, for me, this definition is very strongly depending on the choice of the parameterization. But so that means even if you have the same curve with the same orientation with same integrand, but what if I change my choice of the parameterization? Then a priori, technically, then this number also must change. If you change the integral, if you change the parameterization, right? Why? Because definition is clearly depending on the parameterization. But however, if that is the case, then I think this definition is not ill-defined, not well-defined. Why? Because this left-hand side is clear has nothing but curve and the integrand. So this left-hand side says nothing about the choice of the parameterization. So in order to make sure this is the nice and good definition, then first I will need to make sure this number is actually independent from the choice of the parameterization, right? So yeah, so if not, then this number will actually doesn't make any sense at all, right? Okay, so the first theorem should be like this. The complex line integral is independent from choice of parameterization. So what does it mean? So, well, once the curve and integrand and the orientation curve is fixed, then this number must be the same, no matter which parameterization you choose. Okay, so let me try to prove this. I have a curve. This is a complex plane, and say that I have a curve that looks like this. Since my curve has to be oriented, so yeah, this arrow represents its orientation. So this is a curve, And well, also say that I have two different parameterization of the same curve. First, I will call the first parameterization to be z, and the another parameterization to be u. So z tilde. So well, z. So I have a. This is from A to B, and this blue arrow means this parameterization z, which is xt plus I times t, I times yt, and the green arrow means another parameterization. Well, I am running out of notations, so well, please allow me to use the tilde. Sorry about that. So x tilde plus I times y tilde, and this is defined from the, oh, sorry. I should be using some different letter. So u, sorry. U and U. Okay. So also we are assuming that these two parameterizations are all one-to-one, right? So you cannot go back. So once you start this, so you can only go forward. So this parameterization is mapping this closed interval here, and this guy is also mapping this closed interval here in one-to-one manner. And since both of these arrows, both of these functions are one-to-one, so therefore one of them can be invertible, right? So if I invert this function from here to there and compose it with this guy, then that will going to give us a very nice function from this interval to that interval, right? Oh, sorry, I forgot to put the beta here. Which I will call the phi. Phi of u is t, right? So suppose that I have there is a one-to-one function. Well, since this guy was one-to-one and this inverse of this function was also one-to-one, so composing these two guys will also one-to-one, right? So this is a one-to-one function, which I will call phi, such that phi is a function from alpha beta to a comma b, and this is very important condition. The phi prime of u must be always positive. So what does it mean? So if I travel in this direction, then the function phi will be also increasing from A to B, right? Why is that? Because we are assuming these two arrows, they are both, these two parameterizations are also, they are both the parameterization of this oriented curve. So if I can travel in this direction, then that's going to be traveling in this direction. And same is true for this. So inversion of this function and composition will also guarantees I have this, but then I have this condition. Okay. Okay. All right. Then well, this is very obvious, but also important relation between these two. What if I compose this guy, this function phi by z? If I compose this guy with this, then that is also, well, then that's going to be just this function z tilde itself, right? So this is x phi u plus I times y of phi u, and this is just z tilde of u. This is x tilde u plus I tilde of u. Okay. All right. Yeah. Okay. And let me say this is our integrand, the function that is going to be integrated. So also can be split into the real and the imaginary part. Then taking taking the complex integration, but this time I am integrating this function using this parameterization. Suppose that I am using this parameterization. So from A to B, fzt times z dot of t dt. Hold on, yeah. Okay. And then this is from A to B, u xt yt plus I times v xt yt times x dot t plus I times y dot t and everything dt. So okay, great. Now what? Now I want to use the change of variable. So since this integration is nothing but integration on this line, right? So this is integration along this one-dimensional line over here on the real line equipped with t coordinate. But what if I just pull back this integration by using this function phi? If I take a pullback of this function here from here to there, then well, by change of variable or by taking a pullback, then this integration on this line is going to be now integration on this line, right? From alpha to beta. So then this is from alpha to beta. U of x, then every t now must be replaced by phi of u, right? So this is phi, maybe x phi of u. Now things are getting messy. Phi of u plus I times v phi u. Oh, sorry. Yeah, so yeah, x of phi of u, y of phi of u, and multiply by x dot of phi of u plus I y dot phi of u and now dt is this is my Jacobian d phi du and du. Okay, all right, but yeah. Well, actually, to be precise, I actually need to split this entire expression by real part plus I times imaginary part. But yeah, but that is only going to consume our time. So let me just skip it. Then, and also we have x of x composed with function phi is going to be x tilde, and y composed with function phi is just y tilde, right? So this is from alpha to beta. So u of x tilde y tilde plus I times v of x tilde and y tilde. Okay, and if I multiply this guy by this, then this is going to be just x tilde. Well, I am abusing notation. So this means I am taking the derivative of this x tilde function with respect to u, right? Yeah, sorry, maybe just, I should better say. Plus I times d du y tilde u. And everything by du, okay? This is just chain rule. And oh, voila. So this is what? So this is clearly, according to our definition, this is clearly the from alpha to beta, f of z tilde u times d du of z tilde and everything d, right? So let's see this. Okay, well, this is, well, integration. This is complex integration using the parameterization of z, and this is complex integration using parameterization of z tilde, and they turns out to be the same number, right? So therefore, our definition is a good definition and well defined. In other words, independent from the choice of the parameterization. Just one more thing here. So, well, here, so we are using this condition. I said this condition is very important, but it looks like I have never used this condition in this process of the proof. So how did I use this? How did I make use of this condition? Can you see it? Well, so this condition was actually used because, well, if I do not have this condition, then maybe I was not pretty sure of the order of these two numbers, alpha and beta, right? If this derivative of phi was negative, then the order must be the increasing order of alpha and beta, and A and B, they are like opposite to each other. Therefore, these two numbers could be like beta here down there and alpha on top here, right? Okay, so therefore, so that means that gives us the idea. So that gives us the idea. Even if you have the same integrand function and the same curve, but if the orientation of the curve is reversed, then your complex line integral also is differed by sign, right? So if this is negative, then this number also must be interchanged. Therefore, this entire thing needs to be multiplied by -1 over there. So if phi prime is negative, in this case, then should be negative. Well, please allow me to use the z tilde over here. Must be negative of this. So that means even if the complex line integral is independent from the parameterization, but complex line integral is depending only it's not completely independent from the orientation, but complex line integral is sensitive only on the choice of the orientation, right? So because of that reason, please allow me to use this notation. If I say minus of integral of the integrand function f along with the curve c, but if I say minus c over here, well, this minus c implies that, well, this guy is, well, by our definition of the complex integral, this guy has orientation. Well, this guy is assumed to have orientation. And if I put the minus sign on top of this, then that means the orientation is now being reversed, right? So if reversed, then this integral is precisely the negative of the complex line integral with original orientation C. Okay. All right. So this is about this is the maybe the one most crucial fact on the complex line integral. These are some additional properties on complex line integral. So first, complex line integral is linear. For any two complex numbers, z1 and z2, and for any continuous curve, and z1 times fc plus z2 times g of z is gz dz. Yeah, this is very obvious because, well, just because, right? Also, suppose that I have two oriented curves C1 and C2, and suppose that these two curves, the end point of the first one is the same as the starting point of second curve. Then you can actually consider a concatenation of these two curves, which I would just say C1 union of C2. Then is C1 integral of C1 plus integral of over C2. Okay. Okay, all right. Now, we are ready to, I am finally ready to give you some example of this complex integration. I want to integrate the function 1 over z over the curve C1, where C1 is a semicircle, semi-unicircle on the over this is radius 1, so this is +1, and this is minus. Suppose I want to compute this into this line integral. Well, the first thing that I need to do, just in order to compute this complex integral, is choice of the parameterization, because unless, well, otherwise you can never be able to compute the complex integral. So, and well, in this case, well, as you can expect, one most intuitive and natural choice of the parameterization is cosine theta and sine theta. In other words, z of t is cosine t plus I sine t, sine t, which I will just say e to the it, and t is from 0 to pi. Then this guy is just integral from 0 to pi and 1 over now I need to replace this z by this parameterization. So e to the it, and now I need to take the velocity vector of this guy and multiply by this integrand. And this is just minus sine t plus I times cosine t, right? And everything dt. So this is going to be my integration. So this is just, this turns out to be nothing but just merely a integral of one parameter family of complex numbers. You should be able to do this. Maybe. I guess I am good to replace this ugly expression by I times e to the it, right? Because this guy is this, and taking the integral, so this is going to be that, right? So what now? I have this it and it, they cancel each other. So what I have is just I times dt, and this is just pi times I. Okay. Same integrand, but now curve is now somehow different. So this is the upper half of the semicircle, but this is the lower half of the unit semicircle with radius 1. This time I have my parameterization is zt is this can't be cosine t and sine t. So since the orientation is now reversed, so I should be saying cosine of minus t plus I times sine minus t. I should be better saying e to the just minus I times t. And t is from 0 to pi. Okay? And the rest computation is just same thing. The C2 dz and z is from 0 to pi 1 over e to the I times pi times minus I times e to the minus it dt. So this is just minus pi times I. Okay. So finally, what if I want to compute the complex line integral of this function 1 over z function over the unit circle centered at the origin? Well, in this case, I don't need to compute anything, right? So we know the integral of this guy here. Even if we do not know the integral of this function from here to there, but this integral can be easily obtained by just reversing the sign of this guy, right? So the answer must be 2 times pi I. Oh, just I guess this is going to be our last example for today's lecture. This is a very also interesting one. Suppose that I want to take the integral of this function. I guess the easiest function, just z, the function z, along which curve? Where C is a curve. I should be saying the smooth curve. Yeah, I should better say smooth curve. From Z1 to Z2. So this means that this curve is an oriented curve starting from the point Z1 and ending at point Z2. Okay, so it looks like, well, even if I have not specified I did not specify anything about the curve except from its two endpoints. So therefore, a priori, I should not be able to compute the integral of this guy, right? But anyway, so let me try to compute that. I have very strong feeling that this integral may be independent from the choice of the specific curve connecting these two points. Let Z be the not the A parameterization, parameterization of C. Then C dz Z dz is for convenience, allow me to that T is between A and B. So from A to B, xt plus I times yt times x dot t plus I times y dot t. Everything followed by dt. Okay. I cannot do this. Well, maybe this is going to be my dead end. But no, actually not. So I need to make use of some little very clever algebraic technique here. So, well, can you see this? Actually, this is a function multiplied by its own derivative, right? So you may try to consider this guy as the derivative of the 1/2 times the derivative of this guy's field, right? So, I mean, this is just try to take a derivative of this guy with respect to t and square. If you take a square of this and take a derivative and divide by 2, then you're going to get this. Well, it looks like this is okay. I can make use of the fundamental theorem of calculus. Then you can easily be convinced that this is just xt plus iyt, everything squared from A to B, which is xa plus I times ya square minus xb plus I times yb square and parentheses. Oh, hold on. So because of this condition, this is the starting point and this is the ending point. So it's going to be Z. Sorry, I messed up. Sorry, I messed up. I have negative over here. So Z2 squared minus Z1 squared. Okay. Wow. So I really like this the conclusion of this example, because first, so this sort of gives us the idea that some kind of weird version, complex version of fundamental theorem of calculus is still working in this example, which is very nice. And number two, so there can be some complex line integral, which is depending only on the starting point and the ending point of the curve. And this type of integral is completely independent from the shape of your curve. So as long as your curve has the same beginning and ending point, then you're gonna get the same number. But this is not always the case. Why? Because let me just take a look at this example. So if every integral is path independent, then this guy should be zero. This integral should be also zero. But obviously this is a non-zero number. So that means there can be some complex integral which is independent from path. And there are some other integrals which is depending on the choice of the dependent path. Yeah, well, and we're gonna discuss about that later in maybe next lecture. Okay, see you then.